and Peter Grunberg got the Nobel Prize in 2007 for the discovery of giant magnetic resistance. This is a fantastic phenomenon occurs chromium nickel alloy. What is of interest here is that the magnetic materials are always sought after for industry because of the hard disk that we use today. I'm sure all of you have Wi-Fi, phone, laptop, in one way or another. All that are coated with magnetic materials. Most of them are having this GMR, this giant magnetoresistance. This has been discovered in 1988. You can see that within 8 years' time, IBM has already launched this GMR head. So this is very high sensitive, to read very tiny elements of the memory that can increase your capacity tremendously. If you remember a few years back, maybe 5-6 years back, the iPod just brought a big revolution. Very small size, very high capacities because of all the GMR head. So that is the kind of thing that we are talking about. We need to have a very small device, very large capacity. What does Kryder's say? Kryder's law is commonly called in this area. The magnetic disk area storage has to double angle. That means whatever I am storing today, I should be able to, within the same space, I should be able to store double that by next year. That technology has to improve to do that. So what's happening, you can see from 1950 onwards, 1950, IBM has developed this project called RAMAC project. So at that time, 20 MB per inch squared is what is achievable. This is the first magnetic material being used for information storage devices. Over the period of time, you can see from here we are up to here right now. So there is a linear increase. Kryder law is actually possible. You can see, and lots of different way to improve the magnetic aerial storage has developed. As of now, we are using this GMR head. It can be used for a few more years. And later on, we will be looking at this, what physicists commonly call the superparametric effect. So the superparametric effect is nothing but, you are using nanoparticles to store information, and that is no longer possible because the nanoparticle is so small and then stop interacting with the environment. So you lose whatever you are writing. Obviously, nobody wants to have it. You write something, you believe that to be there in your waters. So that is not possible beyond that limit, and if you want to go beyond, so only one way out is to use molecules for information. Anything smaller than a particle, you have to come down to molecules, and that is where actually the interest has picked up for this molecular nanomagnets. So right now, for example, the single molecule magnet, the manganese field that I talked about, one bit in principle can be used for one molecule. That would again give you to 10 to the 5 times whatever it is achievable today. So we can say like 1 hour if you are able to store data on a tape, if it is coated with single molecule magnet, it will run continuously for a year. That is the kind of increase that you are talking about. So this is basically single molecule magnet on surface. Lots of efforts, lots of research is going on into this, essentially because it's directly related to the industrial application. It's a multi-billion-dollar industry. Information storage devices is a multi-billion-dollar industry. Right. So what are the bottlenecks? That's what I'm going to tell you briefly. And of course, before going into that, I want to slowly teach you a little bit on magnetism, basic things, how it works and all that. That's my entire idea. So this is what has been used in the period of 1960s. Permanent magnets. You have a huge spin at 10 to the power 10 to the power 20. These are macroscopic. And right now we are here, we are using nanoparticles, mesoscopic area. What we want to get is the nanoscopic nanotechnology. Essentially, we want to use single metal atom complexes or even a little bit metal molecular clusters. You can have 10 metals, 20 metals, all that. Wrap that in the environment. Gives you property that you want. So these are all again characterized by the hysteresis loop. I will introduce you later on what this hysteresis means in terms of nanoscopic world, and that is where actually new physics is happening. I will also tell you a little bit briefly about all that. So that's what we are going to focus on. Let's just now go back. We're going to learn a little bit the things which has happened in the past. So what is magnetism? What is paramagnetism? I just wanted to give you a glimpse of that. So molecules that we know, most of the molecules at least we know, are all diamagnetic in nature. Very simple molecular orbital theory will tell you, right? You take hydrogen, dihydrogen, H2. So you have one electron in one s orbital, another electron in one s orbital. You form, when they come together, you have a bonding and an anti-bonding orbitals. So the anti-bonding orbitals takes two electrons. Both the electrons will be up and down. So it's paired. So there is no magnetic moment. The magnetic moment is coming from the electrons. So here, since one orbital has two electrons of opposite spin, completely quenches, no magnetic moment at all is expected for this H2, which are probably very low. So this is a diamagnetic. This is classified as a diamagnetic moment. Right. So these are the energies and all that. So go back. If you want me to give you more examples, probably again, all of you are familiar. Like nitrogen in 2. Again, I can do my molecular orbital theory, right? Assuming that works very well, right? So I have, these are 3 electrons which I have in my valence shell. I do again bonding, anti-bonding, 5 bonding and anti-bonding. I have 6 electrons paired on 3 orbitals, so I have get no one pair of electrons. So that is also diamagnetic. So how do I know my theory works? How do I know that this is happening? Right? So if you believe in molecular orbital theory, if you know that it works, you can believe. Otherwise, you can do a very simple experiment. Just take liquid nitrogen, take a ball magnet, pour it in, and you will see that nothing sticks in the magnet, just everything evaporates. Nothing at all. You can see that. Well, I like to give you one more example to convince that this very simple experiment works. So I'm going to do with the oxygen. So oxygen, what do our molecular orbital theory does? We have 4 electrons now instead of 3, 2p4, and then we started filling now. We are done with 6 electrons. Now we have 2 anti-bonding 5-star orbitals. I'm sure all of you are already familiar with. So 2 anti-bonding orbitals, and if you put 2 electrons in it, so that's the only way to do it. So I get Futuristic. It's a fantastic concept. You can see this 2 pi orbitals. Right? So one electron is in this orbital, pi star, another electron is in this orbital. These 2 orbitals are orthogonal. Why are they unpaired? Here everything is paired because they are non-orthogonal. They overlap each other. The electrons in the orbital overlap each other, they form a bonding. So here, since these 2 orbitals are orthogonal, in the sense like they are separated by 90 degrees, there is no way that these 2 orbitals can interact. So the electron stays individually in each of them. That gives you a spin of S equals 200. That means like 200 electrons. Okay? So this orthogonal orbital concept is very simple. You can explain that even with very simple molecular access to oxygen. And this concept can be taken to any large structure to illustrate the magnetic property of what we have seen. Right, let's do the experiment. So we take oxygen now. Look at what happens. It's paramagnetic. So now I'm sure you are convinced that whatever a simple layman experiment that what you do works. So you just take oxygen is paramagnetic. Very simple experiment you can do to figure out whether it is paramagnetic or diamagnetic. Right, so magnetism, what is the parameter we measure? When I am taking my molecule, putting in the magnetometer, what we call a sweep magnetometer. So you put the molecule in, what do we observe? What do I get out from my magnetometer? Well, that is where I am going to just introduce a bit of maths, bit of equations and all that. The magnetic moment, the magnetic moment magnetization is related to the change in energy level in the field. What field energy level we are talking about? Energy level of your electrons. If I have an x equal to half, if I apply a magnetic field, it will split into 2, minus half will come down, plus half will go up. This is, what is it? Zeeman. This is Zeeman splitting, right? So this is a Zeeman interaction, and as long as I know where my 2 levels are, with respect to the field, I know what is the magnetic moment. That's all this equation is. Change in energy with respect to the field. Then you know the magnetic moment. Well, I need more sensitive parameters. So I could do with magnetic susceptibility chi, which is nothing but change in magnetization with respect to the field. If I apply a very weak field, because when I measure magnetic susceptibility, I always apply a very small field, then I could actually average that to MH. So whatever that we see from this line onwards, I'm going to talk about the magnetic susceptibility chi, which is nothing but what you measure M that is divided by H. So it gives you a better idea of what's happening. Right, so that is chi versus T, magnetic susceptibility. Right? For a paramagnetic compound, this is the expected behavior. You can see that this is the temperature increases, this is low temperature region, the chi value increases in this axis. So what happens at low temperature? It just slowly increases, and then kind of an exponential behavior. As you can see, it exponentially increases at low temperature. What is happening? Why is it happening? Well, if I have a molecule, let's say that the individual arrows represent the spin and per electron of my individual molecule. At room temperature, I have enough kinetic energy. So all the molecules in a given sample will be randomly oriented. I have enough thermal energy to overcome whatever the interactions which are there between them. So I actually have a random orientation of spin, which cancels the overall magnetic moment. So I start with a very small or zero chi value. As I apply field, right? I am applying the field upwards. So everything will tend to align along the field, obviously. Every magnetic moment, electron per electron, try to along the field. So if I apply a magnetic field or decrease the temperature, I can do both. Right? If I decrease the temperature, kinetic energy decreases. So there is no enough energy for the molecule to have a random orientation. So everything try to align along the field as the temperature decreases and the chi value increases. If we go to extremely low temperature, this is what happens. Everything aligns parallel along the applied field. As I said, we are applying a very small field, sweeping the temperature, or you can do the other way around, keep the temperature constant, sweep the magnetic field. Either way, you will be getting a similar behavior.
I'm just asking as a dimension.
Yeah.
So let's say a paramagnetic species only will interact with the paramagnetic species rather.
So when you measure magnetic susceptibility, the magnetic susceptibility comes only from the unpaired electrons. Only they are the only electrons to be contributed. So they will interact only in the sense like they will be interacting only with other molecules or atoms which have electrons. That's the only thing that you can deduct in.
So then of course can we just relate that to metal oxide formation? Let's say iron.
Yeah.
Which will interact with the molecular oxygen that you get fluorescence formation. Similarly, of course, that's why hydrogen and oxygen they don't interact because hydrogen is diamagnetic and oxygen is paramagnetic.
Absolutely. Yeah.
Can we relate that to
yeah, sure. If you can measure the magnetic susceptibility, it can be related. Yeah. So, oxygen I was talking about, oxygen activation is a fantastic area if you are well known in the area. And it works only with metal. Why is it working with metal? Because you need unpaired electrons. Then only oxygen can go on bond. It's not like any other atoms. So, that's what the behavior, the magnetic susceptibility versus T, the chi T versus T, which is called. And magnetism is not new to human being. It's been studied well over the last 100 years or so. So Curie Club, it may not be the Curie that is related with the club. This is Mary's Curie, I believe. This is the other Curie, the other better half of the Curie. And he has proposed a law based on studying the magnetic susceptibility of probably 150 compounds. Then he come up with this beautiful equation. The equation is proposed when all the quantum mechanics and all that we know about Zeeman flooding and all that is not known those days. Still he able to come up with this beautiful equation of magnetic susceptibility is related to the temperature where in that this is basically C by T is inversely proportional to the temperature. This is a very simple equation. This is applicable to S equal to half. So what he is telling is what I just explained. So although it's all pretty much simple to us for now, but it took studying lots of compounds to exactly come with the quantitative way to calculate the time. So when you calculate, you understand exactly what you observe from experiment. So you can plot this data in many ways, the way you want. You can plot the chi versus T, as I have just told you. You can also multiply the chi with temperature and divide by, and then y-axis you can plot. This is chi T versus T. So for a paramagnetic compound, as per the Curie law, it should be constant. You can see the value doesn't change. You can also plot 1 over chi versus T. It should be a straight line passing through the origin, or you can plot mu effective versus T in should be a straight again. Constant. So these are all like way of plotting the data, trying to understand different things. I'll tell you why you have to do different plots in a given set. It's not like any other measurements where you just have probably seen only one way of representing the things. That is the chi T versus T Curie law. That's Curie, France. He got Nobel Prize for his seminal work in 1903. If you wonder what is this is that definitely my handwriting. My handwriting is much worse than this. This is basically a note of Curie. When he was working in France, he was trying to, those days trying to understand the magnetism, like how magnetite, for example, Fe3O4 behaves, what direction the magnetic axis is, how the magnetic flux is. All this are written in French. This is French. So all this are written in French. This is basically his handwritten note on a little bit of magnetism.
What is MKSP?
That's the institute that he has worked. ESPL, institute that he has worked. Right. Moving on from the history. Does it work the Curie law always? Of course, it doesn't. Later, a few years later, they realized that there are deviations. The black line, what we are supposed to see, there are many molecules are showing this blue or the red line, which deviates from the Curie law.
Magnetically dilute.
Yeah. This is only for magnetically dilute systems.
We just don't want these two spins to interact.
Yeah, that is what basically these are all like magnetically dilute systems. So the spins do not, are supposedly not interact, at least according to Curie law. When they interact, they do deviate from Curie law. So that is actually what this Curie-Weiss law is being proposed. So a slight deviation, chi versus chi equal to c by t minus theta. That theta is basically you are taking care of your interaction, right? You see here parameter J, exchange interaction. So when the two unparalleled electrons interact with each other, right, which is not supposed to happen according to Curie law, then you see a ferromagnetic coupling or an antiferromagnetic coupling based on whatever the intercept, whether it is a positive intercept